Well, thank you very much. Thank you for that lovely introduction. And I'm very excited to be here and be able to talk about this interesting topic with you. So I plan to talk about two subjects, which I find very interesting and a surprising connection between them. And really, I'm not going to give a comprehensive treatment of either of them. I'm just going to tell a particular story. So let's talk about puzzles, and in particular, what's known as two-dimensional put-together puzzles. Don't really need to define what that means. It means exactly what it sounds like. You have two-dimensional pieces and you have to assemble them somehow. So this category includes traditional jigsaw puzzles, which we're all familiar with, but there are a lot of other possibilities as well. So there are some pictures of examples. So more often the pieces don't necessarily have pictures on them. And one interesting thing is they can, unlike with a traditional jigsaw puzzle, they can often fit together in multiple ways. One piece can fit into multiple others. And there are lots of interesting examples. These puzzles can be very difficult, potentially. There are even mathematical results saying that problems of this kind can be NP hard or even undecidable. And I want to highlight one particular example, the eternity puzzle. So this was marketed and sold. It's a puzzle with 209 pieces to be fitted together into a dodecagon. And it was sold with a £1 million UK prize, so just over $1 million, €1 million, for a solution. And the designer and the sellers were hoping that they would sell enough copies before anyone managed to solve it, that they would make a profit. So it turns out they were very wrong, actually. It was solved less than a year after it was released by a pair of mathematicians. They won the £1 million. So they applied some real mathematical analysis to the problem, and they used that combined with very targeted computer searches to solve it. So what makes a good puzzle? Of course, that's highly subjective, many different answers. But if we focus on the solving process particularly, then maybe some things that would be nice are it's easy to get started, so there's sort of a low barrier for entry. And then it's hard to solve by brute force search, simply trying all the possibilities, but there are one or more insights or aha moments where you suddenly discover something, and ideally maybe you even discover some mathematical truth, which makes it easier to solve. And of course, there are many other more subjective criteria as well. We probably want it to be elegant and satisfying in some way. And one nice property that I quite like is that the pieces comprise the complete set of something. We'll come back to that. Anyway, so I want to talk about one attempt of mine to come up with a nice two-dimensional put-together puzzle. So here it is. It's called the Garland Puzzle. I actually have some of the physical pieces here. It's an actual physical puzzle. So if we were in person, I would have liked to provide several copies of it for people to play with. Sadly, haven't been able to do that. And I should warn you, I'm kind of going to walk you through the solution of this puzzle, so there will be a little bit of a spoiler, although I'll try to make it not completely so there would still be some enjoyment in solving the puzzle, I think. So anyway, there are 30 pieces, they're all different. The goal is to arrange them in a circular ring, an annulus, and you can see a piece of the annulus here that's started. You want to make a complete ring, and you see the pieces have these jigsaw-like shapes, and adjacent pieces in the ring have to interlock, but you are allowed to leave little holes like this one. And each piece you're allowed to flip it over, to turn it over, and I made these out of laser cut plastic. Laser cutting is a fantastic way to make really, really accurate, nice looking two-dimensional shapes. how might you try to solve this? Well, I mean, if you just literally tried every possibility, there's an awful lot of them, because you have 30 pieces, and so there are 30 factorial possible orders of them around the circle, and each piece can be flipped over as well, so you have another factor of 2 to the 30. So that's an enormous number of possibilities. But of course, you know, no one would really try to solve it that way. You would sort of try fitting pieces together and then try to build something up. So let's think about what this puzzle is actually like. So, and again, I wish I had physical copies for people to play with at this point, but you'll just have to imagine. So each piece has 2 sides, a left and a right side, and there are 5 locations along a side where we have these various decorations. And the types of decorations are, we can have a big sticking out knob, or we can have a big inward hole, which the knob fits into. And also there's a small version, there's a small outward knob, and here we have 2 small inward holes. And I'll denote these by out in capital letters for the large one, and small letters for the small one, and so on. So if you look at all the pieces, you find that each side of a piece has exactly these 5 decorations. It has a big out and a big in and a small out, and always 2 small ins, but in a different order in the 5 positions. So how many possible sides are there? Well, you have these 5 possible symbols, and if they were all different, you would have 5 factorial possible orders for them. But because 2 of them are the same, 2 of them are small n, you divide by 2. So there are 60 possible sides. And remember, there are 30 pieces. So it turns out the pieces are a complete set. So you have 2 times 30 sides, and you have exactly all 60 possibilities. These are sort of the things you would discover if you play with the puzzle, hopefully. And moreover, they're always, the 2 sides of the piece are always paired in the same way. So it maybe seems slightly arbitrary, but it's not. So we always have small in opposite big out, and vice versa. And so it's always you change the type and the size as you go across from one side to the other, except in addition, we always have one position where we have a small in on both sides. Okay, so that's how they're paired. And this doesn't quite actually pin it down, because it doesn't tell you, if I have a side like this one with the 2 small ins, it doesn't tell you which of those 2 should have the other small in opposite it. But if you want to know, there's a specific rule to that as well. It's that you have these 5 possible pairings between the 2 sides, and it turns out they appear in all 60 even permutations across the pieces. So a permutation can be classified as either even or odd, sometimes called positive or negative, and the permutation is even if you can get to it by doing an even number of swaps starting from the identity. Anyway, it doesn't matter if you don't follow that bit. Okay, so if you were trying to solve this puzzle, what would you do? So you might start with a piece and looking what can fit into it. So here's a piece. What can fit in? What can fit on this side here? Now it turns out there are exactly 2 possibilities. Why is that? Because you have the big out and the big in, and those must fit into a big in and a big out the other way around. So, like for instance, here and here, and then so this only leaves these 3 positions where you have 2 small ins and 1 small out. So so the 2 possibilities are that you have the small out here or the small out there. Those are exactly the 2 possibilities for what can fit here. So because I have every possibility represented exactly once. There are exactly two other pieces that can fit, and that's true for every piece. So that already reduces the possibilities, right? So now if you imagine trying to build this up in a ring, one piece at a time, you just have two choices each time. So that's 2 to the 30 possibilities. So it's still a billion. But of course, still you wouldn't actually solve it like that. No one would try to solve it like that. What you would do is something like what's called backtracking in computer science, backtracking search. You sort of try something, keep building it up until if you get stuck, then you go back and make a different choice and try something different, right? And it turns out at this point, if you do that systematically, you could solve the puzzle that way. It might take an hour or so because there's still quite a few possibilities, but that's a perfectly good way to solve it. Some people have, but actually there are more discoveries to be made, which make it easier. So so here is a piece. This is the one I just looked at, in fact, and here I've placed the two other pieces that can fit into it. So this one can fit like that, like I just described, and this is the other one that can fit into it, and I've placed it vertically above like that, so it can fit like that. You turn it round, and I've placed it like that because actually it turns out the other side of this piece can fit on the other side of this one. And it turns out it's always like that. One of the two pieces that can fit on a side, it can also go the other way around. And you know, it's just because of the way I chose to do this pairing, and because it's sort of always the same rule, that's always going to be true. So then I could carry on exploring. So you know, what's the other piece that could fit here, for instance? Well, it's that one. And then there's one other piece that could fit there, that's that one, and so on. And you actually get a little triangle of 6 pieces that could all fit in the various options like this. And actually these are sort of all the ones that have the big out and the big in 2 particular positions, perhaps the other way around. There are exactly 6 of them. And there's no reason for me to stop there. I can carry on trying to place pieces where they could fit. So this is the little triangle I just constructed, and I can carry on placing all the pieces. So this is all 30 of them. And these are all the ways they can fit together. So this was my little triangle. They can fit like this. And then here's another similar triangle over here, and a similar set of possibilities. And this picture actually wraps around. So if you label these points on the edge A, B, and C, then you have to label these A, B, and C, and you should identify A with A and B with B, and so on. So for example, like those 2 pieces on the right between the A and the B sort of also belong on the other side over there to complete this little triangle. And then it turns out when you do that, when you wrap around, you actually have to turn the pieces over physically as well. You have to actually turn them over. Okay, but sort of because everything is so symmetrical, because there's a symmetrical rule behind it, it's kind of the same everywhere, right? I mean, this is the triangle I started with, and then this triangle over here is similar. A similar rule applies. And for instance, you always have 5 triangles meeting at a point, like here, for instance, and here. And again, because it wraps around, so like that is a triangle, for instance, and the missing side of it is here between A and C. So this actually, you can think of it as embedded in the projective plane. It doesn't embed on a sphere naturally, that's the projective plane. If anyone can think of a nicer way to represent this picture, would be nice. But anyway, so now all you have to do is, what do we want to do? We want to find a path that goes along these orange squiggles and uses every piece exactly what, and then joins back again. So it's a cycle. And so, okay, so, you know, you could probably figure that out with pencil and paper. It's a little bit tricky because when you go off the edge, you come back in a funny way, but you can probably figure that out. But there's another secret which makes it even easier. If we go back to this initial triangle that we looked at, so actually I claim, so remember these little arrows are the ways that two pieces can join together, the possible ways. So I want to claim, actually you must either use all three of the red arrows in this triangle or all three of the purple arrows. Why is that? Well, for each piece, for each side, there are just two possibilities, right? So, if I used this red arrow, for instance, then that means this side of this piece goes with this piece. So then what about this piece? Well, the only possibility for it is it either goes next to this or it goes next to this, but this one's already taken, so it can't. So you can't use this purple arrow, so this piece has to join to this one, the red arrow. And then same argument again, this is taken, so this one has to join to this. So you have to use either all three of the red arrows or all three of the purple arrows. And you have to use one or the other because otherwise there's nothing aside. And so of course this applies to every triangle, right? I have my big picture, and every triangle you either use the little squiggles in the corners or the squiggles on the sides. And moreover, you know, you can say some more things. You can't, when you have two triangles next to each other, like here and here, they cannot be both the red configuration, because then I would have a tiny little loop that joins up in the middle. And I don't want that. I want one loop that goes all the way around. And similarly, when you have 5 triangles meeting at a corner, they cannot be all the purple configuration, because again, I would have a tiny little loop, and that's no good. I'm looking for one big loop. Okay, so at this point, there are really very, very few possibilities, right? Because there are just 10 triangles. I have to make a binary choice for each one, and there are all these restrictions that I can see immediately. So there are just very, very few possibilities to try. And you can quickly find a solution, and it's essentially unique. So it's unique up to the symmetries of the problem, and you know there are quite a lot of symmetries because this picture is sort of the same everywhere. So this is one nice way to draw it. It has this threefold symmetry, and because remember everything wraps around. So like this triangle, we have this little red curve here, which really is more natural if you put it on the other side. So if you draw it like that, now we have a complete circle. And so that's the solution of the Garland puzzle. So you know, I don't think this is the perfect puzzle, but I think it's quite a nice puzzle. It's sort of elegant, and there's a process of solving it, and it's hard, but not so hard as to make people give up. So you know, it's kind of a nice mathematical object. So where did it come from? So it didn't come from nowhere, actually, and I didn't just dream it up. Not at all. So it comes from somewhere rather surprising, although maybe not so surprising if you read the abstract. So it comes from bell ringing. And this is the tradition of English-style bell ringing, which evolved in the early 1600s and is still very much alive today. So these are the kind of bells that you might find in churches, and it's a very specific way of ringing them. There are some pictures here. You see they're quite large bells, and they're rung using ropes. So it's actually two things that go together, which evolved kind of in tandem in the early 1600s. It's first of all the way the bells are physically hung in a tower, as it's called. These are bells that are hung full circle, as it's called. So that means that the bell is attached to a wheel and they swing through 360 degrees, mouth up to mouth up, as you can see here, and controlled by a rope, normally by someone standing in a different room below. And then going along with that, there is the particular type of music which is typically rung, which is called change ringing. And it's very different from traditional melodies that most people are used to. It's a lot more mathematical, and the two evolved in tandem. I'm going to try to show you a video. Videos don't always come off so well in these situations, but I'll try to show you a bit, and if it doesn't come across very well, I can show you where you can see videos at the end. Okay, so I hope that was enough to at least give you a taste of what I'm talking about. I'm sure there will be many questions. So by the way, where are these bells? The vast majority of them are in the British Isles, about 5,000 or more. There's now a handful in mainland Europe, quite a lot in North America, and quite a lot in Australia and New Zealand, and a few more dotted around the world. The heaviest bell is about 4 tons. The number of bells ranges right up to 16, and the bells are normally tuned to a diatonic scale. So I'm going to focus on the music, which is called change ringing. So, and I'll try to explain, first of all, what this is like when we just have 4 bells involved. Normally people have a few more, but it's easy to understand with 4. So, so we have 4 bells, and when we write them down, we attach numbers to them. So the bell with the highest note is number 1, and with the lowest note is 4. So one thing you could do, which is what's written down here, is to simply ring them in order in a descending scale. So that would be 1, 2, 3, 4. And then you can just keep on doing that. So that's called ringing rounds. 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. So, okay, but that gets a little bit boring after a while. So what people do is change the order. So one way you could change the order from 1, 2, 3, 4 is to swap the first pair and the second pair at the same time. So we would go from 1, 2, 3, 4 to 2, 1, 4, 3, right? And we would ring first that and then that. And now if you again swap 2 pairs, of course, you would get back to 1, 2, 3, 4. So we don't want to do that. We want to do something else. So what you can do is, for example, swap the middle pair. 2, 4, 1, 3. I won't try to sing anymore. So now we could actually just repeat the same pattern. We could swap the 2 pairs again, the first 2 and the last 2, and then we could keep repeating this pattern of 2, right? And then we can swap the middle two again, and that actually gets me to backwards, 4, 3, 2, 1. And then you keep going, swap both pairs, swap the middle pair, swap both pairs, swap the middle pair. And after 8 steps, you get back to 1, 2, 3, 4. And so this is 8 different permutations of 4 bells. And actually, if you want to think about it that way, it's actually a group. It's a dihedral group of order 8. But of course, how many possible permutations are there with 4 objects? There are 4 factorial, which is 24. So this is not all of them. So one thing that early bell ringers decided would be a fun thing to do is try to ring every possible order. So here's a way you could do that. So right at the end here, when I was about to get back to 1, 2, 3, 4, instead I do something new. And what I'm going to choose to do is I simply swap the last pair and leave the first 2 where they are. So now I get something new, 1, 3, 4, 2, that I haven't seen before. And now what I'm going to do is just repeat that pattern again. So the 1, 3, 4, 2, I've written it again at the top of this column, just for ease of notation, but I'm not repeating it, I'm just writing it down again. And now I just do the same pattern again. I do the same pattern as this first column, swap 2 pairs, swap the middle pair, etc. Up to here again right until the point where it would repeat, and then I do this different thing again, swap the last pair, and then do the same thing again a 3rd time. And it turns out this gives you exactly all 24 permutations, once each. And moreover, what's nice is you come back to 1, 2, 3, 4, where you started at the end. Okay, so these methods, as they're called, have strange names. This one is called plain Bob minimus. It was developed in the early 1600s, and people very much knew and understood that this was all 24 permutations. So if you want to think about it in a different way, you could think I could write down all possible permutations of 4 numbers, 1, 2, 3, 4, 2, 1, 3, 4, and so on, and I could join 2 of them together if I can get between them by swapping adjacent pairs. So normally, they didn't really talk about this, but normally bell ringers try to, when we transition from one permutation to the next, the usual rule that's imposed is each bell can only move by at most 1 position, to the left or to the right. So that if you impose that rule, it comes down to saying you just have to swap adjacent pairs, maybe several at a time. And the reason for that is related to the physics of how the bells are rung. Actually, maybe I won't get into that, but I could talk about it at the end if people have questions. So anyway, if you swap adjacent pairs, then you could swap the first pair or the last pair or the middle pair, or you could swap 2 pairs like this. And I join 2 permutations by a line or an edge if they are related in one of these ways. And so if you do that, you get this. So in modern mathematical terminology, this is a Cayley graph of the symmetric group. And this particular Cayley graph is sometimes called the permutahedron. And so what did I just do? So plain Bob minimus was a Hamiltonian cycle of the graph. In other words, it's a path that winds around, visits every vertex, every permutation exactly once, and comes back to where it started. So how long would this take to actually ring? So what you do is you just ring 1, 2, 3, 4, then immediately ring 2, 1, 4, 3. Just ring these permutations one after the other. So with 4 bells, it doesn't take very long. It takes less than a minute at the usual speed people would ring. But well, we know n factorial grows very rapidly, right? So if you were to try to do this with 12 bells, it would take over 30 years to do this. So people don't do that, but people do quite often do it with, for instance, 6 or 7 bells. With 7 bells, you have 5,040 permutations. It takes about 3 hours to ring. People do that quite regularly. It's called a peal, P-E-A-L, and it's kind of like a marathon of bell ringing. The equivalent of running a marathon somehow. Okay, so let's think about the mathematics a bit more. So of course you can carry on drawing these calligraphs, permutahedra. This is the one for 5 bells, but as you can see, it's going to get very big and complicated very quickly. So maybe not the best way of thinking about things. And moreover, so bell ringers actually like to impose more structure. They like to ring methods that have a lot of structure to them, because it makes it easier to remember and makes it more elegant and so forth. So here is a particular bell ringing method that I want to focus on. So this originates in the early 1700s. We know about it thanks to a gentleman named Benjamin Annable, and in modern terminology, it's called Annable's London Surprise Minor. Again, these very strange names, which you don't need to worry about. So we have 6 bells. So we always start by ringing them in the order 1, 2, 3, 4, 5, 6. And now I have this rather complicated looking pattern of swaps, which you don't need to follow in detail. But first of all, I swap all 3 pairs, 2, 1, 4, 3, 6, 5. And then there's just some pattern. And the pattern lasts 24 permutations. So here I have 24 different permutations. And now the rule is going to be, at the end, after that pattern, I'm allowed to do either this pattern, where the 2 pairs kind of in the middle swap, or I'm allowed this different one. Have a pair there and a pair at the end swap. And then you repeat. So the rule is you do this pattern of swaps for 24 permutations, then you do either the blue thing or the green thing. And then again, you do this pattern starting from what I ended up with, like 1, 5, 6, 3, 4, 2, or the other one. Starting from there, I do this pattern of 24. And then at the end of it, again, I'm allowed to choose either the blue thing or the green thing, right? So you do that block, either the blue thing or the green thing, that block, either the blue thing or the green thing, etc. And so the question then, is there a Hamiltonian cycle using this method? So is there a way to visit all 6 factorial permutations exactly once each, ending up back where I started at 1, 2, 3, 4, 5, 6, using this method? So is the question clear? So again, just in terms of raw possibilities, how many times do I have to make this decision between the blue or the green? Well, I have 6 factorial permutations in total, and this block has length 24. So I have to make the choice 6 factorial over 24 or 30 times. So if I were to just try everything, there would be 2 to the 30 possibilities, which I guess you could just try all of them on a computer if you want to do. But there's no need, and early bell ringers realized this. So here's some analysis that makes it much easier. So, and again, you don't have to follow everything on this slide if you don't want to, but I will briefly explain how it works. So this weird pattern that I started with, it turns out it's symmetrical in the sense that if you divide it into 2 halves, the second half is the same as the first half reversed in terms of the pattern of swaps. Okay, so like near the beginning here, we have this motif where the 2 bells in the middle stay put, and similarly at the bottom, we have the same motif there. Okay, and moreover, if you look at this first half, it has a special property, very special property. If you classify each permutation by, firstly, where is bell number 1? Which position is it in? So here's bell number 1. It's in first position, second, first, second, third, fourth, etc. And in addition, you write down the parity of the permutation. Remember, a permutation is even or positive if you can get to it by doing an even number of swaps. Right, so the identity 1, 2, 3, 4, 5, 6 is positive, and then the second one, I did 3 swaps to get to it, so that's actually negative. So if I write down the position of number 1 and whether it's positive or negative, then it turns out I have exactly all the 12 possibilities here. There's a 1 plus somewhere, there's a 1 minus somewhere, 2 plus, 2 minus, and so on. Okay, so not a coincidence. So because of that, it turns out, and because all these blocks of length 12 have the same structure, all you need to do to solve this problem is make sure that you get in these positions at the beginning and end of my block and the corresponding places every time I repeat. You must get all the positive or even permutations that have a 1 at the beginning of them. You must get all of those type of permutations represented at the beginnings and the ends of these blocks exactly once. And if you do that, you'll be done. And actually, this is a special case of, why would you be done? Because, well, for example, suppose there was a repeat. Suppose I did this, and suppose somewhere I had the same permutation twice in 2 different places. Well, you would have to have bell number 1 in the same place for both of them. So maybe bell number 1 is in the 4th position, say. So that would be here or here. And also the parity must be the same. So maybe it's like 4 plus, right? So that means there are 2 of these half blocks where I have exactly the same permutation in this particular place, 2 different places. But then that would mean if you follow back the pattern, it's the same pattern of swaps. So I would have to have the same permutation at the end of the block as well. I said I didn't have that. So that's kind of the argument. And actually, this is a special case of an argument that works for any subgroup. So the same argument would work for any subgroup of the symmetric group. This is a subgroup here, and any traversal of the cosets. So this is an example of a traversal of the cosets. And once again, bell ringers understood all this in their own way, actually a long time before mathematicians did. So what it comes down to is you have 30 possible blocks that need to be joined together. So these are all the blocks you can get by writing this particular pattern of swapping, but starting from any even permutation with 1 at the beginning. So there are 60 of those permutations, but you divide by 2 because you have 1 of them at the beginning and 1 of them at the end. So really what it comes down to is there are 30 of these blocks to be joined together. And each block, you're allowed to do it backwards. You're allowed to start from the bottom, unless the permutation is going upwards. So really only the permutations at the ends matter. You can forget about everything in here, and you can also forget about the number 1 at the beginning, right? Because that's always going to be at the beginning. So really you have 30 of these little cards that you can imagine making, and you have an even permutation of 2, 3, 4, 5, 6 at the beginning, and then a corresponding one at the end. And what is the corresponding one at the end? Actually, it turns out it's you always just reverse it. So 2, 3, 4, 5, 6 goes to 6, 5, 4, 3, 2, etc. And so, for example, these two would be allowed to be slotted next to each other because this blue pattern is one of my 2 allowed transitions. Okay, so you can probably see where this is going at this point. Not too hard. So this is equivalent to the Garland puzzle. So these permutation blocks are equivalent to puzzle pieces, and the correspondence is a little bit confusing because you kind of have to invert the permutation. They have the bell numbers 2, 3, 4, 5, and 6 that appear here, and I'm going to label the 5 positions on the puzzle piece, 5 locations, by the numbers 2, 3, 4, 5, 6. Here it actually doesn't matter how I did it. I could label them any way I wanted. And then there's also a correspondence between positions in the permutation over here and these decorations that I can put on a side. And the correspondence is, well, it's like this at the bottom. And here it does matter. It's not arbitrary at all. It has to be exactly like this. So here are the 2 puzzle pieces that correspond to these 2 blocks. So for example, if you really want to know, so here, for example, so this is on the upper side of this block, which corresponds to the upper side of this puzzle piece. Bell number 6 is in the 2nd position. And if I go down here, 2nd position corresponds to a big in. So that means I should put a big in location 6, because that's bell number 6. So that corresponds to that. Okay, so it's just a translation. And yeah, and it turns out it just all works. I mean, you could check the details for yourself, but the 2 the 2 translations that I'm allowed to do in bell ringing world over here just correspond exactly to the 2 ways, the 2 pieces that can fit into this one. And so, for example, like the big in and the big out always have to swap over, right? You have to put a big in into a big out in puzzle world, and that corresponds to the fact that both of my allowed transitions over here both have the 2 bells at the beginning swapping over, and 1st and 2nd correspond to out and in. So anyway, it just works. So there's essentially a unique solution, which is in direct translation to the puzzle. One of the remarkable things here is that arguments like this were known to bell ringers from the 1600s onwards. And in particular, this particular problem I talked about was very well understood and solved certainly by the early 1700s. And of course, they didn't go via the Garland puzzle, but everything I told you about the Garland puzzle with these triangles where you either do the purple rule or the red rule can be translated into the world of bell ringing, right? I mean, there's nothing complicated about the translation, really. And they understood all that. They understood all this argument, and in some way they understood about the positive and negative permutations and so forth. And on the other hand, group theory and subgroups and Lagrange's theorem and all this sort of thing was developed by mathematicians considerably later in the 1800s. So there's really no question that bell ringers discovered group theory long before mathematicians did. And interestingly, I could go on for ages, but the people who were doing it were not necessarily technically trained. I mean, some of them were, but some of them were signal box men and manual labor, some complete mix. Anyway, so finally, let me tell you about an open problem. So one can make an argument that this is the hardest known specific constrained Hamiltonian cycle question. I mean, okay, I mean, if you really set out to make a very difficult problem of this kind, you can probably make a harder one, although, you know, even then it's not totally obvious how you do it, because we saw with the example of the eternity puzzle, it's not necessarily straightforward to know how difficult one of these problems is. But anyway, this one, lots of people have tried and failed, including me. I've spent a lot of time on it, and lots of other people have, but it deserves more attention. So here's the problem. It's very simple. 7 bells. We start from 1, 2, 3, 4, 5, 6, 7, as always, and we do this particular pattern of 6 permutations. So it's, I can show the slide again later if you want to see it, but it's you just alternate between this pattern of changing, where the one in the 3rd position stays put and the other pair swap, and this, where first one stays put and 3 pair swap. Alternate between those until it would come back to the identity. So 6 permutations, and then at the end you're allowed to do either this or this, and again you repeat each time you choose. You do this pattern of 6, choose the red or the blue, then this pattern of 6, choose the red or the blue, etc. Right, so the question is there a Hamiltonian cycle visiting all 7 factorial permutations and coming back to where you started using this method? So this is an open question. By the way, if you allow yourself a 3rd option here, then the answer is yes. This was solved over a century ago by Bellwingers, actually using some quite fancy group theory, which once again was the group theory involved was kind of known to Bellwingers a long time before mathematicians identified it. And so finally, well, in my folly, I decided it would be amusing if I could convert this unsolved question to a puzzle. So this is what I spent quite a lot of my time working on at ISOM. So this is an equivalent puzzle to that unsolved problem. So there are 840 pieces like these ones, every one different. And again, they're kind of the complete set of something. And you have to fit them together into a ring, like the Garland puzzle. It has a lot in common with the Garland puzzle. You have to fit them together into a big ring. And in addition, there are 840 identical pieces like this, which have to go vertically and slot into these holes. Of course, I won't explain the whole equivalence here, but it is equivalent. And there are these sort of fancy crenellated knobs for some reason, which are necessary. And it would make a circular ring about 3.5 meters in diameter. And I actually made these physical pieces, and sadly I don't have them with me thanks to the pandemic, but I actually have a set, and if anyone's really keen I can give you the patterns. It's quite expensive to cut them. So there we are. So if you want more information on bell ringing, just search YouTube for change ringing and you'll find lots more videos like the one I showed you. If you want to find bells near you, there is something called Dove's Guide, as I said, especially if you're in the United Kingdom, but there are others as well. Yes, anybody, any ideas how to solve this last problem I just told you, or ways to popularize it to get more people interested? And I'm very interested in ideas for the perfect, especially 2-dimensional put together puzzle. I mean, let's find one where to solve it, you just need to rediscover some theorem of mathematics. And I'm sure there's something like that out there. So that's it. Thank you.